Finished the last movie by pointing out that alkanes float on water. And that's worth repeating because it's part of a nice little mnemonic that my colleague Joel Loveridge came up with, and that is that alkanes are like witches. They float and they burn. And those of you familiar with Monty Python's Holy Grail witches scene will recognize that. Those who are not familiar with it, well, maybe you should go and watch Monty Python and the Knights of the Holy Grail, one of the funnier movies made. Anyway, talking about alkanes burning. Okay, alkanes undergo combustion reactions, and you should be familiar with combustion reactions from GCSE and so forth. Right, combustion reactions where something reacts with oxygen and all of the atoms in the original combustible molecule turn into the oxides. So carbon becomes carbon dioxide, hydrogens become water. You will, of course, remember at different things that when you have an incomplete combustion, you don't make all carbon dioxide, you make carbon monoxide. I'm not that fussed about that right now. So anyway, CnH2n plus 2 plus oxygen goes to CO2. It's worth just generally balancing that, seeing as how we have a general formula there. So we have N carbons in the original alkane. That will give us N carbon dioxides. We have 2n plus 2 hydrogens in the original alkane, where every water molecule, of course, needs 2 hydrogen atoms. That means that we will get n plus 1. N plus 1 is, of course, 2n plus 2, all divided by 2. So we have, therefore, in total on our product side, N carbon dioxides. Well, there's 2 oxygens in every carbon dioxide, so that's 2N. And N plus 1 waters, there's 1 oxygen in each water. So total number of oxygen atoms, 2N plus N plus 1, or 3N plus 1. And then, of course, each oxygen molecule and the reactants, which is where all the oxygens come from in this case, each oxygen molecule has 2 atoms, so you'll have a total of 3N plus 1 over 2. Oxygens. Not really worth memorizing that. I've seen some people who tell their students memorize it. Often enough, it's just easy enough to balance it. But just to quickly apply it, propane N is 3. So therefore, you're going to get 3 CO2s, N plus 1 or 4 H2Os, 3N plus 1 over 2, well, 3 times 3 is 9, plus 1 is 10, over 2 is 5. Butane, N is 4, pop that in, and we get 4 carbon dioxides, 5 waters. But then you look at the oxygens, 3N plus 1 is 13, over 2 is 6.5. We don't really like those 6.5s unless we're talking about heats of combustion per mole. So therefore 2C4H10 plus 13O2 goes to 8CO2 plus 10H2O. Just multiply through by 2 all the way. It's worth mentioning with heats of combustion, I mean, this is not the thermochemistry module, but if you list out the heats of combustion for each of those first 10 straight chain alkanes, you'll see that they increase as one would expect. And once you get past the first couple, methane, ethane, propane, then very, very, very nice little observation that pretty much the heat of combustion increases by about 700 kilojoules per mole for each carbon atom. So that's shown in that last column. That's the taking the heat of combustion, the middle column, divided by the number of carbons, and that gives you that nice little relationship there. So something worth knowing is, again, once you get past those first few, then the curve settles out as you go from one alkane to the next one, a increase in terms of the amount of energy that you get out of about 700 kilojoules per mole for each carbon atom.